All right. Let's give everybody a second to join in. Welcome, everybody. It's a pleasure to have you all here. How's everybody? All right, cool. All right, let's quickly start. We can start doing some intros. So hi, everybody. I'm Romain from Polymorphic Capital. To give you a quick bit of context, I have a sort of math and computer science background. And I first learned about FHE like back in 2015 from university professors that were telling me that, it was too complicated and it wasn't going to happen. So I guess things changed, and that's an amazing thing. And that's why I'm so excited to be here with you all today, to get some insights from sort of super cool people building super cool things in the space. We've got an exciting schedule packed. I'm gonna give a 2-second chill about polymorphic, and then I'll hand it over to to the people that are why we're here. So in a few words, Polymorphic Capital is a pre-seed to Series A Web3 VC fund. We've got an amazing multidisciplinary team that's looking sort of all across the spectrum. But the two areas we hold sort of dearest and nearest to our hearts are social related projects and cryptography and FHE. We started looking into FHE last year and sort of humbly published some research articles that we'll share later on in the resource channel. But this led to a conversation with Gurgen from Fair Math. I'll let them explain what they're up to in a second, but we're really excited to be co-hosting with them. We've got really cool presentations lined up. In order, we have Fair Math presenting first. Then we have Junbum and Young Hyung from Crypto Lab that are going to be presenting their SDK to train FHE classifiers. We have Ahmad, a senior scientist from OpenFHE, that's going to be showing their library in action. Next up, there's Nir, a cryptography researcher from IBM, and they're going to be introducing HE layers, or HE layers. He'll also tell us how he wants us to pronounce that one. And then these are basically modular layers that fits together to make FHE DevX really accessible. And last but not least, we have Christian from Mind Network explaining how they're using FHE and stealth addresses to solve some major Web3 privacy concerns. So with that, super excited to hand it over to Gurgen for Fair Math.
Yeah, thank you, Romain. First of all, it's a pleasure to be here. I think it's a great event. And my name is Gurgen. I'm from Fair Math. And let me share my screen. I would like to share some information about us, what we are building. I think we can start, yeah? Or we have to wait a few minutes because I see that people
are still joining, but I guess you can start.
Okay. Do you see my screen?
Yep.
Great. So Fair Math, we are open source oriented company, and we are working in FHE field. Our main focus is to development of FHE technology itself. Our main goal for the nearest year is building open source comprehensive FHE components library, which in our opinion should significantly simplify application development. The problem with such library that we believe it's impossible to build such library inside only one company, and we need to community engagement to build such library. To solve this issue and to engage community, we developed the first, I believe, of our fully automated FHE challenges platform, FHERMA. We launched it in November 2023. And what is FHERMA? FHERMA is an open platform for hosting fully homomorphic encryption challenges. We developed it as a joint project with OpenFHE teams, and the first version of the platform supported only OpenFHE library. But we are going to extend supported library, and our next challenges will support not only OpenFHE, but at least Latigo library. On the platform, we have two types of challenges, black box and white box. What one of the most interesting thing about FHE, it's opportunity to one party to prove that this party has some algorithm for other parties without revealing any information about algorithm itself. And this idea we use for our black box challenges, where we publish challenge, we publish some encrypted test cases, and we require from participant side to proceed encrypted test cases and upload on the platform only final result, which allows us to decrypt, compare with expected result, and make some scoring. So in this case, not necessary to upload source code. It's just needed to upload ciphertext, which can be considered as some kind of proof. In this case, we usually can measure accuracy, but also we can measure criterions like levels. But in these cases, it's not possible to measure performance, which may be important for some cases. For challenges, when we need to measure performance, we developed white box challenges. In this type of challenges, participants upload source code of the project. On the platform side, we compile, build, and measure performance. Usually for white box challenges, the main criteria is performance. As I mentioned, we launched the platform in November with 3 initial challenges, with matrix multiplication, logistic regression, and sign evaluation. I would like to consider all challenges, deadline has passed for all challenges, and I would like to consider one of the challenges and result of one of the challenges, namely logistic function challenge. This challenge was built with CKKS FHE scheme. We had a vector with batch size 2045. And for this challenge, we had 2 test cases. The first one was pretty simple. The second one, the information about it you can see on my slide, was more difficult because we expected to have not more than 4 multiplication levels. Usually, to solve such kind of challenges, it's possible to use some polynomial approximation methods. So, for example, Chebyshev approximation method can be considered as one of the options. And inside OpenFHE library, there is a method for approximating any one variable function. On this slide, you can see the initial logistic function with Chebyshev approximation. So you can see that it's not a good approximation. And based on our error evaluation formula, Chebyshev method basic Chebyshev method provide not more than 88% of accuracy. At the same time, the winner solution in this challenge provide more than 96% of accuracy. And it's really amazing for us, because not for us, for for all community, I believe, because it shows that this approach can work. The first challenges, as I said, is finished, and we are going to launch new challenges this week. New challenges will include ReLU function and image classification challenge. We already added it on the platform, but the official launch will be at the end of this week. We are going to publish at least one challenge every month, maybe often, but it will be, we expect to have at least 25 challenges published this year. And a few important notes I would like to mention about the platform and about our approach, which is, in my opinion, is very important. The first one, that we are, as far as we open source oriented, and we about fairness, all submissions on the platform we consider as submitting under Apache license. So which means that we don't have any restriction about ownership. We don't have restriction about non-compete, confidentiality, etc. We are committing to publish the winner solution in open source form also under the Apache license. And we don't transfer any ownerships. So each challenge will have the developer name. Currently, this week, we are finalizing validation process for our first challenges, and we will officially publish the winner name and winner solution also this week. The validation process is just needed to verify that submitted result is correct from the point of view when we just need to check that submitted result on the platform without any some prohibited methods, etc. So that's all from my side. As I mentioned, as I said, it's a pleasure to be here. And Roman, please.
Okay, very cool. So essentially, you're crowdsourcing functions to build across libraries to sort of further all the ecosystems of OpenFHE, Latigo, and all the further participants down the line. That's super exciting. And can you tell us a bit how to get started? Do you have a toolkit? Do you have an SDK that makes it easier?
Currently, we have some challenges published on our platform, and to participate in these challenges, we support two libraries. We will support for next challenges two libraries, OpenFHE and Latigo. For each challenges, we will provide some template project. And currently, to participate, to work with our platform, it's just needed to build library to prepare environment, for which we will provide all necessary scripts, etc. And and also template projects will help all participants to just focus on developing components.
Nice, that sounds amazing. So people can focus on the heart of the matter. Which type of audience would you say this is for?
In our general vision, we believe that to develop components, to develop function, it's not needed to be a cryptographer. And for example, if you develop some components for machine learning, you have to be an expert in machine learning. Because in fact, when we are developing FHE application, FHE components, the only thing you have to know about FHE, the basis you have. So for example, you can do addition, you can do multiplication. Depends on the scheme, you can do a few additional operations and some limitations. Like if you work with leveled encryption scheme, you can do not more than, let's say, L multiplication in row. That's all which is needed to know. And so in our general vision, we believe that it's not needed to be a cryptography expert. But currently, as far as you need to work with FHE library, despite the fact that, let's say, for example, OpenFHE library provides pretty simple to use API. The same about Latigo. Unfortunately, you need to have some expertise in cryptography to be able to provide some context, etc.
Okay, all right. And I assume long term the sort of the barrier to entry gets decreased as you make the tooling better and is all sort of like comes together. And so now, for example, the functions from the challenges that have been finished are accessible through the OpenFHE library, or how can I then use this ReLU function that's going to be programmed on Ferma?
About finished challenges, we finished challenges, which means that we chosen the winner. At the same time, we didn't close the opportunity to upload solutions because we have fully automated scoring evaluating process, which allows to users just to come to the platform, upload solutions, and compare with the winner solutions for the moment, because we have real-time leaderboard, and just in seconds you can upload your solution and see the see your place on leaderboard.
Ah, cool. So real-time results. And last question from my side. How is this sort of real-time leaderboard and how is this sort of challenge platform an upgrade to sort of what currently exists in like bounty challenges and stuff like that?
It's a good question. Thank you. About currency bounty programs. So I know Zama bounty program. I know about challenges like iDash platform. So the main difference, let's say, from bounty program, from Zama bounty program, the first one is it's fully automated. So it's not needed to wait 3 months. It's excluded any human factors. We believe that here we need to have competition-based approach, which will allow us to have at the final really good component with good quality, and we already saw it on the platform when we, for example, for logistic regression function, we saw, let's say, one result from one user about 90% of accuracy. Then in sometimes other users uploaded new result with better accuracy. And then this competition approach finally helped us to have what we have. Yeah, and also difference from as a competition-based approach, as a bounty, as a challenges platform, I think it's license limitations and restrictions, because from our side, we're fully transparent for audience, we have a program committee, etc. And we don't have any restrictions, just only requirements to consider Apache license as the main. More details we published in our terms, and at the same time, again, just to make it more clear, more transparent, we published our terms in GitHub, so everyone can just go to GitHub and follow every change in our terms.
Okay, cool. So fully embodying transparency. I guess the test-driven nature of your challenges mean that people can iterate faster and sort of have a leaderboard to compete against, gamifying the experience a bit. Super cool. Thanks for sharing. So we have one more question from Alina, who's asking, are the prizes only for the first place? And will the presentation be available publicly? Before I give that to you, Garian, yes, everything will be public, and we'll also compile a list of resources and stuff like that to sort of put everything together in one place in the chat. So Garian, first place prizes?
Currently, for the first challenges, we mentioned that we will have only first prizes, but we considering option to have some prize for the second place, because we have pretty similar result, pretty close result from the second place and the first place, and we would like just somehow to say thank you for participants. So currently, officially, we have only first place result for our initial challenges, and we have winners. This is Aikata. Maybe she joined us, but anyway, we will publish it. And also, we are going to have the second prize for the first challenges, but more detailed information we will publish this week. And for the next challenges, we also will have not only first prize challenges, but also at least the second.
Okay, amazing. Garian, Fermat, thank you so much for presenting. We're now gonna hand it over to Junbum and Young from Crypto Lab. Show us how to make privacy-preserving classifiers. It's exciting.
Yeah. Can you hear me?
Yes.
And thank you for your time. And so I'm Junbum Shin, CTO of Crypto Lab, and he's Young, my colleagues. So today, first I will share my screen. So can you see?
Yes.
Yeah. So the goal of our presentation is that Now, the fully homomorphic encryption FHE is ready to use, and it is easier than you think. So you can now use it in practice. I think that this talk should be interesting. So my talk consists of three parts. The first one, I will introduce our new privacy-preserving automated machine learning service using fully homomorphic encryption named AutoFHE. And then I will tell you how can you make your own applications using fully homomorphic encryption using our HEAN SDK, or software development kit from Crypto Lab. And then we will introduce how you can make your own application for training and inference using our SDK. And then I conclude with some key takeaways. Yeah, automated machine learning. Yeah, actually, I love this service because I'm not an AI expert. I'm a crypto expert. I'm very good at privacy preserving everything, but not AI itself. So sometimes I use the AutoML service to train some models because they give us a very great trained models. And no AI expertise is not required. So it's a very beautiful cloud-based service for non-AI experts, but there are some restrictions for the AutoML service because, for example, when there is some secret photos, some confidential, some highly private information, can I use that? I can just utilize the service only some non-private public images only. I can't send such images to the conventional AutoML service. So this is the motivation of our privacy preserving machine learning service named AutoFHE. So now we can support both the training and inference. So for the training part, the client, before send our data to the server, they encrypt it using the fully homomorphic encryption. Because of FHE, the data can be trained on the server side without decryption. After the training, the server send the trained model, and after decryption, I can utilize it. Let me show you some example. So this is our AutoFHE service. So if you can select your data set, then now we are ready there. So if I push this button, and all my data will be encrypted and then uploaded to the server. So I push this button, and there is a progress bar. So my encrypted data is uploaded to the server side. And the training now happened on the cloud side. Our current implementation is just based on GCP, Google Cloud Platform. Since the training takes about 4 minutes, so I will introduce some others before that. So, and then I will back. And so the training now it's running. And for the inference, I think that it is also better than shows you some live demos. So the privacy preserving inference is very easy. If you select some photos, the encrypted data encrypted and sent to the server, the inference is done on the server side and sent back the result. And after decryption, the client can see it. Oh, it's very fast. So it just takes about 0.34 seconds. And if I select this one, so yeah. It said that, yeah, it's a civilian cross. So it's a military beaker and civilian cross classification. But one important thing I want to emphasize is that it is not toy. Actually, you can use any kind of the photos, for example, in the Google Cloud. So if I select some photos and yeah, it's an image from the Google search. It also works for the civilian cars. For example, I will try to use this one. It does not look like cars, but anyway, it is not a military one. Yeah, So yeah, it gives a right result. So now the fully homomorphic encryption is ready to use, especially for the image classification case. So what does it mean then? Fully homomorphic encryption gives a lot of guarantees about the privacy. Now, let me say, think about the privacy preserving AI outsourcing case. If we use the conventional cryptography, then there will be no problem for data transfer and data storage, but when they do the data analysis, data should be decrypted. So there's a possibility that my data can be leaked by some hackings or some malicious insiders. But if you utilize the fully homomorphic encryption, you don't need to worry about that because everything is encrypted and only you holds the decryption key. Everyone knows that the encrypted data without decryption key is useless because no one can decrypt. So it means that fully homomorphic encryption solves compliance, data breach, and governance risk because the data owner holds the decryption key. They don't need to worry about where my encrypted data is. They only need to protect their decryption key. So it's a very, very important technology for the compliance, data breach, and compliance governance, minimize the governance risk. So actually, our OTFA service is based on our HEAN SDK. So HEAN SDK is a software development kit, and we support the C++ and Python APIs, and also we support the GPU accelerations. There has been a lot of built-in machine learning and AI functions, and classification and image classification, we already haven't seen, and also we support text classification, and also support linear model, triensemble, and statistics. Among them, in our AutoFHE service is using this functionality. I think that maybe the training is completed. Yeah, so yeah, the training is completed. So if I push the model evaluation button, actually the trained model will be tested using the validation set. So if I select the Fulton data, actually the training data is 80%, testing data is 10%, validation data is 10%. And actually the result is a little bit strange, but yeah. When you think about the training data, actually for the human eyes, they look similar, but for the machine AI point of view, they are very different. So this gives us from this result. And then if I go back, then actually you can download and use the trained model. So now my colleague Youngyan will show you how can you utilize the trained model in our AutoFHE service. Youngyan, please.
Hello, I'm Young Kim. I'll continue with the presentation now. With AutoFHE, you can download the model trained in an encrypted state and apply it plain text. By clicking model download button, you can download the YAML file and metadata JSON file. At this point, the downloaded YAML file is our decrypted model that was trained in an encrypted state in AutoFHE. Also, by clicking on download sample code, you can download a sample Jupyter file that we have pre-created. Now let's go through the Jupyter file that together. Since all the details instructions are already written in the file, I'll be brief with my explanation. Step 1, to first download the required packages and modify the path. And step 2, you should modify the path where the model was downloaded, current directory. So fix this and modify the path where the image to be tested are located. I'll try to use the same image zoom used in AutoFHE in-front test. So fix. And then, as you can see, you can check the image here, directory. And step 3, we use VIT model to extract picture from the image as we did in AutoFHE. And first step is to load model trained in AutoFHE. You should modify the model name in here. We set model name as FHEllo, cyclone, and fix it. And finally, you can classify the image to be tested. As you can see, military and civilian, and fix it. And you can see the image is military and civilian. So now let's talk about harness K. AutoFHE utilize our harness K, so now I'll explain how to use harness K in code and apply it to your application. Harness K is public on GitHub and can be found by searching header. And taking a quick look at README file, the currently released version supports only the Linux environment. For Windows and Mac user, we ask you to use Docker. Likewise, it doesn't support Apple chips. Additionally, we recommend the environment with more than 30 gigabytes of memory. Now I'll explain how to build a header. As mentioned earlier, we will proceed with the building using Docker. And the basic settings are as follows. You can use any Docker image, but I put the basic Ubuntu image. Let's look at each command. I will start update apt. Due to time constraint, I'll proceed with demonstration using a Ubuntu Docker container where the base packages have already been installed. Then download necessary packages such as Git and Python. And next, clone the header GitHub. And set pip in. While it's not mandatory to set up pip-imp, I would recommend doing so. And finally, and finish by installing the included build file, pip install ham, and pip install ham SDK. It's done. Now you know how to build it, and I'll explain how to use it. It will take some time to download, so I will show you the Docker container I prepared. In the README file of the cloned header directory, there are ways to learn it through simple commands. Oh, sorry. However, I provide more detailed instruction on how to use it. Oh, sorry. Oh, I'm sorry. Okay, let's start. The code in this file is based on the lambda-py and vi files. First, load harness K and generate key to train model in encrypted state. I created the key in advance, so it is parsed, but when creating a new one, you should change it to true. And load transformer. In this demonstration, we use the vi model to image clip for image classification, but you can switch it to various models to fit the data you have. And I will demonstrate by classifying MNIST file as an example. So download MNIST file and extract the features. This was also made and saved in advance. So load save data. And then before encrypting the data, set hyperparameter for training. You can fix batch size, efforts, and running rate, and whether or not to use less error, extra. And encrypt the data. And after that, make classifier instance. Finally, you can train model. Once the model is complete, you can check the information about the trained model. The currently released version can only use CPU, so it takes a long time to train large data. If you want to use GPU version, feel free to send us an email.
Yeah, thank you, Yang. So we tried very hard to finish our presentation in 15 minutes. So yeah, so now we have shown that we have introduced our AutoFHE service and also explain how can use the downloaded model from the AutoFHE service even you use in your application. And also we have shown how can you download the HAN SDK to build your own application and how to make it and how to use it to build new applications. So actually, the sample files and the presented file will be shared after this presentation. And there are several key takeaways. The first one is that, so that's the most important. Fully homomorphic encryption, many people say that it's too slow to be used in practice or something like that, but actually it is not true. For the inference, it takes about just 0.3 seconds, but if you accelerate more, then it can be completed in 0.1 seconds. So, and for the training, it takes about from 4 minutes to several hours. It depends on the number of data. But if data has some values, then maybe one day training is not that a big deal. For example, in the GPT case, it takes the training time is more than several months. So it depends on the value of the data. So if you want to have some data, you want to protect the but you still need to utilize that for the AI training, then now FHE can help them. So FHE is ready to use in practice, especially for the image and text classification, linear models, pre-ensembles such as XGBoost, and many kinds of statistical functions. For the statistics case, when the time for the analysis for the 10 million data, usually it takes less than 5 seconds. And in fact, add some more hardware, it can be the 10 million data computation can be completed in just 1 second. So I can say it is ready to use in practice. The second one is that actually our HAN SDK will be released. So, and now it is in the beta version, but if you want to try, then just contact us, then we can share our beta version for your test. And using the SDK, if for your research and testing and development, you can build your own FHE application using our HAN SDK. And as Yang said, when you do the analysis, do the testing, we strongly recommend you to use our GPU accelerations because it shows a very much performance improvement. Actually, the NVIDIA RTX 4090 is just $3,000. It is relatively cheap, but it gives you at least 30 times faster performance than CPU version. So we recommend you to use it. Yeah, that's all. So FHE, welcome to FHE world. FHEllo. Yeah, right. Thank you. Any questions?
Yeah, thank you both. Thank you so much for presenting this. It was really cool to see the UI, see you sort of like pass the data through and see the sort of a bit of time of training. Out of curiosity, could you give us a bit more information? So the data set that you were training on to classify the military and civilian vehicles, sort of how big is this data set?
Here. So in our text civilian paramilitary vehicle case, actually we tested that, and for each class, 100 images is enough for the trainings. It actually shows a very good performance, as I shown in our Google image search case. But if we use some other data set, for example, our skin cancer examples, each class needs some at least 400 images for each class. So actually you can find the example in our AutoFHE demo page. And in that case, it consists of 4 classes. Each class has 400 images. And in that case, the training time is maybe 20 to 30 minutes. something like that. But also, if you add more image, then the time should be longer. But since in our AutoFH service, it is combination using the Google's Vision Transformer and the Vision Transformer already shows the very good performance for small images need to be required for the boost performance training. So actually, in our thing, you don't need to train, for example, million images for the training because all the basic things already trained in the Vision Transformers. And it is also the same for the text classification case. There are many great transformers for the image classification and text classifications. You can utilize that.
Okay, very cool. And another question from me, and then I'll open it up. So at some point you downloaded the model. Does the whole training happen with encrypted weights and model as well? And it then decrypts, so you download the encrypted version and decrypt it sort of on the browser side? Or are the sort of weights and models public as well in the server?
Yeah, so in our setting, the most important one is to what kind of data is sent to the server side. So in our case, the transformer is done in the client side. So the transformer is over the plain text data and the extracted features, only the extracted features are encrypted in the Fully Homomorphic Encryption and it can send to the server. In the server side, actually they can't see anything, but so the model parameters, actually they don't know the model parameters because it's a result of the trainings. So they can't see anything. And after the completion of the training, they just send back it. So the server have no information. And so in our image classification inference case, it's a case that the model in the server is encrypted and the data in the client from the client is also sent to the encrypted. So it's an inference result over the encrypted input and encrypted model. So server can't see anything. Perfectly privacy preserving inference.
Okay, great, thank you. And we have a question from Gurgen in the chat. Do you have some estimation about the release dates for the SDK?
Yeah, we expected the SDK. Actually, it was planned to release in the last fall, but it is postponed. Maybe next quarter.
Next quarter. Okay, awesome.
But if you urgently need it, then you can share our beta version, of course.
Okay, good to know. If anybody wants a sneak preview and start using GAN SDK, you know who to talk to. Is there any other questions? Feel free to speak up or send any questions through the chat. This question from Alexander. So the whole data set is encrypted?
Yes.
Yeah. There we go. No information leakage. That's really cool.
Yep, sure. Everything is encrypted and only the client holds the keys.
Okay, so
Perfect.
here an interesting sort of like follow-up. Is it sort of a fully homomorphic thing, or are you using some just homomorphic encryption and sort of like partial homomorphisms and stuff like that?
We definitely need the fully homomorphic encryption because the addition and multiplication both are required.
All right, awesome. Thanks, Alexander, for the question. Anybody else? Okay, Janbam Hyunghyun, thank you. Sorry, there is one last one. Have you experimented with CNNs?
Yes. Oh, but yeah, so actually we have an implementation for the CNN inference and trainings, but actually the time for the CNN inference and training is just lower than the Vision Transformer based one because in the Vision Transformer, the only thing you need to fine tune is train the MLP layers, because it is defined in the Vision Transformer, so it is easier to fine tune. But if you train the full CNN layer, it takes some more time because actually it depends on the depth. But if you think about the performance, actually the accuracy part, actually Vision Transformer based one shows a much better performance than CNN based one. That's why in the AI community, most image classification works now, they are just using the transformers. They do not use the CNN based ones.
Okay, interesting.
Yeah, the accurate model in a reasonable time.
Okay, awesome. Thanks, Vivek. And then last question from Claudio, and then we'll move on. What is the bit precision in the operations?
The precision is almost the same as the plain text one. Actually, the result is in our research paper presented in the last year's ICML for the oral presentation. Actually, it is interesting. For the best case, actually, the encrypted model training result is 0.5% better than the plain text ones, because some kind of the randomizations during the training. But in the worst case, the performance degree decreased about 0.5 seconds. So the gap is 0.5 seconds, sometimes better, sometimes worse.
All right, cool. Guys, thank you so much for the presentation. We'll link all the resources that they presented in the group chat after the presentation.
Good.
And we now get a talk from Ahmad presenting Open FHE. So Ahmad, floor is yours.
Thank you.
Thank you.
Sure. Hi, everyone. Can you see my screen? I start sharing.
I can't see the screen.
Okay, interesting.
Here we go. Nice. Now we got it.
Okay. Oh, you still can see it, right? I enabled presentation mode.
Yeah, we can see it. We've got presentation view, but we can see the screen.
Okay. Okay, that's great. So, hi, everyone. My name is Ahmad. I'm a senior scientist with Duality Technologies. I'm specialized in Fully Homomorphic Encryption, implementation, and also applying it to solve real-world problems. Thank you for inviting me to give this talk about OpenFHE. So I'd like to introduce what is the OpenFHE library, the capabilities, the schemes implemented, and some of the features in this talk. So first of all, OpenFHE is an open source library. It's written in C++ 17 standard and launched in July 2022. And it's the successor of a previous library was known as Palisade. So now OpenFHE.
Sorry, Ahmad, please.
Yes.
It's better if you change the view of the presentation, because we are like viewing a splitting form of the presentation. Maybe in display setting that you have at the top, you can change the view so it's more convenient for the attendees.
Really? I am not. Display settings.
Swap.
Is it like this better?
This is much better. Thanks, Jose.
Thank you.
Okay, this is better. Okay, got it. So OpenFHE, as I mentioned, it's the successor of Palisade and includes capabilities it's built on projects like Palisade, FHElib, HEM, what was presented before, and FHE. So these are all FHE libraries, and OpenFHE built on top of them. It also includes several new design concept ideas. So here, present the main features. It's like the hallmarks of OpenFHE. First, from the cryptography perspective, we assume from the beginning that all the schemes that are implemented in OpenFHE should support bootstrapping and scheme switching. Bootstrapping means a way to reduce the noise after it gets accumulated during computation. So it's like a refreshing procedure. And scheme switching means a way to switch the encrypted data from one scheme to another. I'll touch more on this later in the presentation. And from the performance perspective, so even though in the previous presentation, FHE looked to be very fast, but for generic computation, it can be a bit slow. So And in order to circumvent this challenge, we believe the best approach is through hardware acceleration. And OpenFHE includes what is known as hardware abstraction layer that facilitates offloading some of the heavy FHE computations to different hardwares, GPUs, FPGAs, ASIC, and so on. And from the usability perspective, we want to make sure that using the library is simple. So there are many maintenance operations. Here I'm giving examples such as modular switching, key switching, bootstrapping. These are automatically invoked by the library so that the users, especially the ones who don't have deep knowledge in cryptography, they do not need to worry about it. So this is all hidden in the APIs. And also another component, which is providing a way for the user to write code in some high-level language and having a compiler or a transpiler to transfer or translate this code from any high-level language, could be Python, could be C++, into an FHE-friendly or compliant code. So these are the main hallmarks in OpenFHE. From the cryptographic capabilities, so FHE, OpenFHE includes efficient implementations of several FHE schemes. And here I want to touch on like 4 families. The first one is known as the PFV scheme, and this is ideal for integer arithmetic. The second one is BGV, similar to PFV. Actually, they share many similarities between themselves, and BGV is also suitable for doing integer arithmetic. So if your problem includes integer data, probably PFV, BGV are like good options to look into to implement your problem in FHE. The third scheme is known as the CKKS, and this one is ideal if you want to do computation with real numbers, like machine learning, for example, or complex numbers, even arithmetic. So in that case, you can use CKKS, and this particular scheme in OpenFHE, due to the use of CKKS in machine learning, we also include in the library its approximate bootstrapping. So that means you can do almost unlimited number of arithmetic operations, whether it's addition or multiplication. So basically, you can implement any function or any algorithm using this scheme with some challenges. The other family, it deals with binary data, like mostly it's for binary data or low precision integers, like 4-bit integers, up to 8-bit maybe, and lower than that. So this family includes the FHE scheme, the CGGI scheme, or the TFHE scheme, and also a new variant known as LMKCDEY. So all these names come from the surname of the authors. So you don't have to remember them, but just mentioning here for the reference. Okay, so these are the main schemes that are currently implemented in OpenFHE. Also, from another cryptographic capability related to multi-party extensions. So we do have a threshold FHE for BGV, PFV, and CKKS. And what that means is instead of having only single user, like having the data, you can have multiple data owners, and they can run a threshold FHE scheme among themselves to encrypt their own data, like individually. Each party encrypts it on its premise, and they send their encrypted ciphertext to an evaluator, which can do some computation over these ciphertext, and the result will be sent back to the users who can enroll in what we call threshold decryption or distributed decryption to basically decrypt the results and learn insights from it. So this is threshold FHE is used for multi-party, like when you have multiple data owners. We also have a feature called interactive bootstrapping for CKKS, and that means, again, in the threshold CKS, if you have two parties and they want to refresh a ciphertext, they can do it together. They can run a protocol, interactive protocol. It's a single round protocol, and it's much more efficient than the single user bootstrapping, which is done on the server. Also, OpenFHE includes proxy re-encryption for BGP, PFV, and CKS schemes. And by this, I mean delegating the decryption from one party to another. So suppose party Alice has a ciphertext and she wants another party, Bob, to decrypt this ciphertext. So this capability is included using proxy re-encryption. Basically, you switch the key from Alice's key to Bob's key, and so on. Also, a very recent capability added to OpenFHE, which is the scheme switching. So currently, OpenFHE supports switching between CKKS ciphertext and FHE or TFHE ciphertext. And this allows us to evaluate non-smooth functions that are like not friendly with CKKS, but they are friendly with FHE or TFHE. And due to what we call functional bootstrapping, this is a feature in the binary family of FHE schemes like FHE and TFHE. They allow evaluating a function over the ciphertext while it is being bootstrapped. So basically, in a nutshell, you can switch between CKKS and FHE TFHE as of now in OpenFHE. Here we have the support matrix capability that shows multiple existing libraries in the literature and the supported schemes. And here, what I want to highlight is in OpenFHE, we almost include implementation of the main FHE schemes. And here by main, I mean like cryptographically secure, efficient, kind of, and adopted or widely adopted by the community. So in OpenFHE, we have implementation for BGV, PFV, CKKS bootstrapping, DM or the FHE scheme, CGGI or TFHE, and also threshold FHE, like the multi-party case I talked about, and the proxy re-encryption. A note here related to the BGV bootstrap. By the way, BGV and BFV bootstrapping are almost the same. We do have prototype that exists, but it's still not part of the release.
Sorry, Ahmad, I'm going to jump in 1 second.
Sure.
To have time for 1 or 2 questions, you're
Yeah,
at the
sure.
3-minute mark.
So in the chat, let's see.
Sorry, you still have a few minutes, but 5 essentially, and then we'll have time for 1 or 2 questions.
Okay, 5 minutes, got it. Okay. So I'll present here some key facts about OpenFHE. The current version is 1.1.2, released in December last year, and designed by, as I mentioned, authors of Palisade, HLib, HEAN, and a few libraries. It's the successor of Palisade. It compiles, this is important, with the homomorphic encryption standard. It's not an official standard, but it's the one that is widely adopted by the research community. OpenFHE is offered under the 2-clause PSD open source license, making it easier to wrap and redistribute OpenFHE in products. It's supported generously by DARPA. Also, it's a community-driven open source project. Currently, Google Transpiler, which is a tool to convert high-level programs written in C++ to FHE compliant or friendly programs. So Google Transpiler uses the TFHE implementation in OpenFHE, and also OpenFHE is affiliated with non-focus stable of open source projects. The design paper of OpenFHE, if you like to read more about the capabilities, it's available on ePrint and also on the ECN website. These are the authors, the main contributors of OpenFHE. Like OpenFHE, if we look at it, it's built in a modularized way, and it consists of these 5 main layers. The lowest one is the primitive or math layer that includes the mathematical structures that FHE deal with. On top of it comes what we call lattice or polynomial layer. And on top of that comes the crypto layer that implements the schemes. And on top of it, the layers that the user can interact with, known as the encoding layer and the application layer. So encoding layer for encoding the data to be compliant with the FHE schemes, and the application layer is to actually implement the problems you are interested in OpenFHE. Here, I just want to highlight that our vision for OpenFHE is we have here OpenFHE in the center, and it would support multiple hardware backends for acceleration. Currently, what is supported is CPU and AVX vectorized implementations, and there are some underway projects for GPU, FPGA, and ASIC acceleration. And on top of OpenFHE, there will be SDKs and high-level capabilities such as matrix arithmetic, Python SDK, and Google Transpiler. So Google Transpiler is already supported, Python SDK already exists, and we are still working on the matrix and Node.js SDK implementations. And finally, for the application support, there will be, like currently, we are working on supporting generic ML applications for inference and training with OpenFHE. So I think I can stop here if I took most of the time, and maybe I can take some questions.
Thanks, Ahmad. Super cool. We have one question in the chat from Maria asking, does OpenFHE include the advanced mode of CGGI? So that's leveled mode plus circuit bootstrapping.
Yes, it does. It does. The circuit bootstrapping, I'm not sure. I'm sure that it includes the normal mode where you bootstrap after every gate. For the circuit bootstrapping, I will need to check that.
All right. We can, Maria, we can get you an answer in the channel later on this then.
Yeah, maybe offline. Yeah.
Anybody else? Okay, then a question for me. So how easy is this to pick up as a non-FHE expert? How does the sort of the user-friendly mode, how far is it going to sort of deviate developers from their habits?
Yeah, like as I mentioned, we do have like I'm not sure, like you can build applications using either C++ or Python. So the library itself is built in C++. You can definitely extend it and build your own application. Also, we have a wrapper to use it inside Python. Like here, I'm showing a demonstration of how to basically initialize the library. Like here, this is an example for CKKS scheme, setting up the parameters and enabling the cryptographic features, generating the keys, defining your data, encrypting them, and doing some evaluation. So you are free to use whatever tool you like, whether it's C++ or Python. Also, if you want to use the binary version of the FHE family, You can use the Google Transpiler to write your code in a high-level language, C++, and it will convert it for you and run it under FHE, basically.
Okay, great, cool. I guess this one seems like a slightly sort of lower level or sort of more closer to the cryptography of it.
Yeah,
But it's kind of cool to see the gears turning as well a bit more. We've got a last question from Claudio. Do you have a table with performances for single processors? I'm assuming you don't have this here.
I do not have it now, but in the library itself, if you go to the OpenFHE, and this is the resource page, so we do have like a benchmark folder. You can run the benchmarks inside OpenFHE. You can choose single thread, multiple threads, and see the performance for all these schemes I presented.
Okay, awesome. Thank you, Ahmad. Thank you so much. Claudio will get you that table in the channel below. And there's one more question, but we are running low on time, so we will post this one in the channel, Alexander. But thank you for the question. All right, so now introducing Nir from IBM. So
Hello.
Nir, is it HE layers or HE layers?
HE layers.
HE layers, awesome. Take
Yes.
it away.
So yes, thank you for hosting me here. Let me share my screen. Okay, you're supposed to see my screen right now, which is great. Let me know if not. And can you see my mouse pointer?
We can see it.
Okay, perfect. So I'm Nir from Nir Drucker from IBM Research, and I'm working in the AI security group on an SDK called HE layers, HE, not he, because homomorphic encryption. And today I'm going to talk about scalable and flexible packing using tiled tensors in really high level, because this can be a tutorial of 3 hours, and we only have 20 minutes. So I'm trying to keep it simple here. Basically, IBM was and IBM Research specifically dealt with FHE since it was practically invented in 2009 by Craig Gentry and Shia Levy. Since then, for a decade, they worked on an open source library called HElib, which provided them FHE capabilities as an open source for the community. And then somewhere around 2019, 2020, we understood in IBM Research that there is still some gap from using the low-level cryptographic primitives to go to higher level applications, basically application developers and data scientists that were interested in using and leveraging the technology, or try the technology, understanding its capabilities, where we lack the capabilities of understanding all the details that the FHE require. And this is why basically IBM decided to start and develop this HE layers framework that I will present in a second. And let's start from here. So this HE layers is basically the name come from the layers, and I think also in the OpenFHE talk before, we saw that they also have the layers. So that's where the layers of HE layers came from, and the understanding that every layer is important in this chain, and every layer contributes something different, and it won't be possible to capture everything in one just a simple layer. Originally, the library was started on top of the HElib library, open source, but it was we increased its capabilities to work on top of many other libraries like Hyan, OpenFHE, Latigo, Seal, and basically every other cryptographic library that provide FHE capabilities. In that sense, HELS is basically allowed or can be run on different hardware like GPUs, CPUs, and even on optical processing units, which is a cool new trend that we are working to learn and understand. And currently we are participating in a project called Phoenix, in a European project together with companies like Optalysis, to understand how to leverage these optics into getting some performance leverage. But the idea is that there is still a gap from these third-party HE libraries is that we have an open FHE to get into the data scientists and application developers knowledge of PyTorch or TensorFlow or any other machine learning or AI libraries, that and this gap need to be addressed. And basically, that's the main idea of FHEllo. I'm not going to go deeper into every one of these layers because it's going to be hard for me to do in 20 minutes. But I will try to understand why it provides good capabilities and why it should be used. So first thing is scale. Scale is something that is super important for us in FHEllo. And if we look on the past decade or so, and there were many developments in the FHE world, there were new skills that came out with great performance and great potential. We see fascinating techniques that are being developed around the world. And we see that the performance to perform FHE computation is going down from the, I don't know, 10 to the 9 or even higher than that was originally presented in Gen 3 original work to something like milliseconds for performing multiplications or rotations. So it's really amazing that we can go as low as this, and probably will go even lower than that with ASICs and the optical units and different hardware. On the other hand, when we talk about AI or we talk about machine learning, we are taking the models, we are dealing with models of extreme sizes. So if we started to work or to implement FHE with models that are super small, with 2-3 layers of neural networks with hundreds of parameters, today we are talking about transformers that has millions or sometimes billions of parameters that we need to deal with. So we have these two activities going hand by hand. The performance of FHE goes down, but still the model size increases. So we need to somehow manage this gap in order to provide them great activities and potential for the data scientists and application developers. So let's look at it from a qualitative timeline. Data is very qualitative. I just place it so we get a feeling here. So in 2008, we know that we had CryptoNets to perform around 3 layers of neural network with 45 seconds, something like that. We also had logistic regression, who actually was developed a little bit before that, but somewhere around this year, it was already available. And then after several years, we got it down to 3 layers, not only us, people around the world, to 1 second. So we see that it become practical to evaluate neural networks. And in 2021, we know that we already can do networks like AlexNet and SqueezeNet that involve 20 layers and 38 layers over FHE in a matter of minutes, which is super fast and exciting. And the 3-layer neural network got down even to 0.56 seconds here, and later on it was go down to 0.045 seconds. So we see a lot of improvement in the performance, but on the other hand, we see the network that we want to perform and to evaluate, like in inference and also in training, but mostly in inference today, growing and growing in size. So from SqueezeNet, we go to ResNet 18, and then we go to ResNet 101 to show capabilities like zero-shot learning, and also from ResNet with 152 layers over a large data set like ImageNet with 60 million parameters in size in a matter of minutes. We are talking about orders of dozens of minutes or something like that. So it's super cool. We see the performance going down, and we see the size of the network going up, and we see that the target of transformers of 100 million parameters or billions or more parameters is getting closer and closer to be practical, and this is very exciting, at least for me. Now, the question is, if the model grows so much higher, how can a data scientist still utilize the low-level primitives of FHE to perform encryption? And this requires special knowledge and special capabilities that usually are not existed in his toolbox. So let's take, for example, a motivational challenge of someone who wants to run a neural network model. They want to run it on fully homomorphic encryption. That's the goal of this data scientist or application developer. They want to basically do nothing. They just want to take the Onyx file or a Chaos file and to provide it to the, I don't know, SDK like ours, and and magic, wait for the magic to happen. And but also we want to have a tweak. We want that this model will support different batch sizes. So the batch size is really unknown at the beginning of the runtime, and we want to have some flexibility. How can we really do it? Okay, and the goal, of course, is that it will run in efficient time and that it will be simple to code it. So in order to make something simple, I need to make it very complex. And I'm going to do something a little bit technical that will look complex, but in the next few slides, but we will see that that's exactly the main purpose of FHEllo. This is what we are going to simplify. So let's look on it. The concept of SIMD, single instruction multiple data packing, was introduced long time ago, not even in the hardware domain, but also not in the FHE domain, but also was ported to the FHE domain, and it is being used by many schemes like TKK, BGB, BFB, etc. The idea of SIMD is that the ciphertext can pack multiple data in one ciphertext. Like here, we pack the values x0 to x7 in one ciphertext and w0 to w7 in one ciphertext. And we can perform element-wise multiplication. So, and we do that with one multiplication instruction of homomorphic encryption. So that's the idea of SIMD. We can, of course, leverage that, and this is well-known data, to perform other operations. We can also use rotations, for example. If we have x0 to x7, we can move x1 to x7, and then the x0 goes here, rotation by 1. We can do rotation by 2, by 3, by 4. And we can use these operations to perform more complex functions, like rotate and sum. We take a vector ABCD, we want to sum all of its elements. What we are going to do, we're going to rotate the vector by 2, so CD goes here, AB goes there. And we are going to add them together, and we get these values, then we rotate again by 1. No need to remember the detail, just to understand the complexity that is going to grow. And by another addition, we got the sum of all the elements duplicated 4 times. So that's a really cool algorithm that we leveraged SIMD for us. We can do inner product in really the same manner. An inner product is a critical thing in neural network, in logistic regression, in other type of operations that we would like to do. So same thing for inner product. What we want to do is to multiply and then perform the rotation sum algorithm to accumulate the data and get the inner product result. So, but the question starts to become complex, and this is where it is not as easy as it seems like when using SIMD. What happens if we want to perform 3 inner products, x times w 3 times? Then we need to decide how to pack the data inside different ciphertexts. So here we place the x0, x1, x2, one next to another, and we decided to pack them in a column-wise. So every column contains 1x vector, and same thing for w. Now, of course, we can multiply one with each other with one multiplication, but then we need to do the rotation sum, which would require costly rotation operations. Alternatively, we can do it, we can pack the data using rows. So every row is going to be packed in ciphertext. Once we pack every row in a ciphertext, then we can basically still use one multiplication to multiply the data, but we then need to add this ciphertext instead of doing the rotation sum algorithm, and therefore we don't need to do any rotation in this computation. So we see that using different packing really affect the performance. And what happens if the dimension of the batch size is bigger than the dimension of the vector x, or the vector dimension x is bigger than batch size? How flexible is the packing option that we chose? Is it flexible? How can we handle scale in that situation? And does it really affect anything? Like, does packing really matter? And the answer is yes. Here we see different packing options, and we see the latency and the memory and how they are changing over these different packing options. And we see that it's not always goes that you want to choose one of the most left or most right options. You might want to choose the middle. Of course, latency and memory are not the only options to consider here, only metrics. We have throughput, we have power, I don't know. There are others to consider when considering the different packings. And here there are only few settings of packings. So we see that packing is very important. So going back to the questions that we start with, I mean, if we want to support different batch sizes in our application, do we need to program an FHE application with different packing for every scenario and every different batch size that we need in order to achieve the optimum that we wanted to achieve? And this is something that to answer this is very complex. For that, we need automated tools. And the HLF is exactly providing this capability. It allows you to move between one packing to another using automation that is developed inside the library, and which simplifies these capabilities for the users. So again, the plan was to use the user to write something as simple as a keras code, something like that. Maybe do some operation, compilation, fitting, I don't know, whatever the data scientists want to do. And then decide on how the packing, what the packing will work best. And we want to achieve that using something that is called tile tensors. So that was kind of an introduction of why it's important. And again, in 5 minutes, we'll try to explain what tile tensors is. So tile tensors basically is a way to represent the packing of a data using a schematic way, using a notation, a language. So here we have a matrix of 5/6, and we want to pack it in ciphertext. These are tiles that represent ciphertext. Each has 8 slots. So we can represent the ciphertext in one way, like having 2/4 matrices, small matrices. And in that sense, we will use this notation. The matrix original size was 5 and 6, so it's 5, 6 here. And 2 and 4 are the dimensions of the tile. So this is how we represent this notation. And we can use a different shape to pack the data in a completely different way. We can take this matrix 5/6 and pack it in ciphertext still that has every ciphertext has 8 slots, but we are packing the data in a different way, which allows us to perform the computation in a different way. And the advantage here of using tile tensors in the notation and the understanding that there are so many packing and the way to enumerate them is that we can design a code to work on tensors and not on ciphertext. So users don't need to program every ciphertext, say take 1 to 5 put here, 6 to 11 put here, etc. They need to say take this matrix, put it in another tile tensor, and we go from there. And this is what our SDK is providing: the ability to work with high level or high dimensional tensors in a really easy way to do that, and to have a packing of limits, because the user doesn't really need to know what the packing is; it just need to use the packing once it gets it. Okay, so this is an example of a more complex packing. I just give the picture due to the timing. The idea is that we can perform matrix multiplication in a really easy way using this notation of tile tensors. And where is that? Sorry. And if we look on the literature, we see that many of the papers in the past try to define the new packing method. You have the naive method, the dense method, the sparse representation, the tax representation, the active packing, so many different names for packing. But once we use tile tensors, we can basically just use the same notations for all of them, which really simplifies the work. And then we can create a state machine that go from one shape to another and define the operation between shapes in an easy way that allows us to automate the process. So tile tensor shape has much more notations than the one that I showed you, but I wanted to get you the feeling of what tile tensor is. So going back to the layers of HLF, we have the third-party libraries that we rely on. Then we have some abstraction layers. So everybody who wants to work directly against these libraries can use the abstraction layer and move between the libraries to test them. And we have a circ layer that basically get a layer of get a circuit of gates and optimize this execution of them over this library. We have the tile tensor layer that I just described, a packing optimizer, and an AI layer. And the idea is that the data scientists and the application developers doesn't really need to be familiar with all of this. They just need to provide us ONNX files and get the results. In the website, you will be able to find different demos, neural network, XGBoost, ARIMA, logistic integration, etc. And to summarize, HLF provides scalable and flexible packing using tile tensors you can also experience with the tile tensor directly. Every layer here has its own API, so people can decide what level of what granularity of knowledge they own and want to own in order to play with FHE applications. So it's possible to use tile tensor directly or through the packet optimizer or through the AI level layer. And it enables easy and flexible SDK for writing FHE applications. And in a high conversion, read Onyx, chaos, run under FHE, even big input. So I think that's exactly my time, right?
Thank you, Nir. Right on time. Love the haiku. Yeah, thanks for that sort of great and like deep dive into SIMD. I am very glad you guys are abstracting this from me. I never want to see it again, with all respect.
Okay.
So no, I'm it's super.
I completely understand. That's exactly the idea. That
Okay.
people won't need to mess with it, but they know that there is we
Awesome.
hide this complexity for them.
But yeah, and so you were mentioning that there's different levels of complexity, so you can either choose to sort of get your hands dirty and sort of go into all of that, or you can just basically feed in your Onyx files and all of that.
Yes.
Can you interface directly with like Python, C++, or sort of like languages, or do you have to just provide model files?
So we have several ways to do that. Here in this example, you can see that to use HLS, you can simply do what is this? Just a second. Here. Sorry. I find it more easily in a second. Here, this is what you have to do. In your Google Collaborator notebook, you can do install PyHLS, import PyHLS, and basically that's it. You get PyHLS. And then if you want to encrypt model or do stuff like that, you could just say, I want a neural network model and init from files from JSON file, HE file, etc. And of course, you can find more information on our website. We have demos, we have installation, and everything else is discussed on our website.
Okay, awesome. Thank you. Yeah, we'll definitely share that with the group afterwards. We've got a question from Robert. What does the AI layer do? That's actually a great one.
Okay, so basically we have two different options. We can allow you to provide Onyx files. So you take from PyTorch, you take the Onyx files, then we translate it directly to tile tensors and start to do stuff. But in some cases, you would like to use some predefined, optimized objects that we know that we can optimize a little bit better. You know, sometimes you have more generic solutions, sometimes you have more specific solutions. So, for example, in homomorphic encryption, you have a random forest. Random forest is not easy to do, not always easy to do in scale. But instead, there is a HE-friendly model called completely random forest, which is not optimized in the PyTorch, but it is implemented through the AI layer. It provides results that are kind of similar to the original random forest result, but are HE-friendly in an HE-friendly way. So you can start from a predefined models that we created for you that got some more optimizations than just going directly through the Onyx.
Gotcha. So support and optimization for all the AI stuff that doesn't come easily otherwise. Very cool.
But for now, we hope to make everything easy for Onyx, but it will take a little time.
Okay, makes sense. If anybody else has any questions, please write them in the chat or feel free to speak up. Just another one for me, because you put it in haiku form, so it's very easy to sort of ask about. Even big input, do you have some sort of benchmarks and some sort of like an idea of what's big input?
So like I mentioned in the timeline, we already implemented ResNet 152 over ImageNet, which requires 60 million parameters, which never, think about it, 60 million does not fit inside one ciphertext. One ciphertext has, I don't know, 65K slots, then 60 million will fit in many ciphertexts, and then you need to manage the movement between ciphertexts and do everything. So this is one example. If we go to LLM, then you know the sky is the limit. We start with 110 million and go to 7 billion and more. So
yeah.
So I'm not saying that it's something that is, you know, if we take 7 billion parameters and stack it on HTL, probably it won't work out of the box today because we are still developing and trying to go forward with the process. But the idea is that for models like ResNet, we know that it works like with 60 million parameters and for this kind.
Super cool. We have time for one more question. But otherwise, very cool. What am I going to say? Yes, the notebook you shared, everything like that. We'll try to put this in the chat afterwards so people can play around in their own time. And
Sure.
if there's no other questions,
Thank you. I love to
thank
be
you very
here.
much, Nir. Thanks for being here. All right. And last but definitely not least, let's bring up Christian from My Network to give us a blockchain spin on things.
Hi, everyone. Thanks for having me. Great presentation so far. Thanks, Romain. So we'll start off with, make sure my screen share works. Cool. All good?
Yep, we got you.
Great. Thank you very much. Okay, cool. So today I'm going to present about My Network. So My Network is a zero trust network for Web3. So we're one of the first tokenized FHE projects in Web3, bringing this new era of end-to-end encryption to multiple Web3 applications, including AI. So today I'll give a brief overview of our framework, and then I'll go into some of the applications, and I'll tell you a little bit about us in the meantime along the way. So the project is a little bit over a year old. We all, the founding team, are PhDs in computer science, cryptography, specializing in FHE. And we had this idea of basically adding a privacy layer, privacy and security layer enabled by FHE over data in Web3. So the current problem in Web3 is that all data is public. Web3 was made for public data. There's less privacy in Web3 than there is in Web2. So that's a problem. If you think that Web3 will eventually be the ultimate version of the internet in the coming years, that would mean under its current infrastructure that all of your grocery shopping, all of your app subscriptions, your streaming subscriptions, everything that you purchase is public. It's available and everybody can see it through your wallet address. So this is something that has to be solved, and some of the key opinion leaders in the space, like Vitalik Buterin and Sergey Nazarov of Ethereum and Chainlink, respectively, have talked to this problem, have spoken to it at length. And so our first product was an FHE data lake. And so a data lake basically would take in semi-structured, structured, and unstructured data, meaning we could combine off-chain data with on-chain data for a multitude of applications. And obviously run third-party compute on that in data without having to decrypt it, one of the features of FHE. So one of the applications was, think of combining your credit score in the Web2 world with your DeFi activity in Web3. So any DeFi activity that you've done, borrowing, lending, trading, swapping, combined with your in the real world credit score for a comprehensive risk profile for underwriting loans, either in Web2 or Web3. Another use case was in decentralized physical infrastructure networks, which is the industry in Web3 that combines IoT with blockchains and smart contracts. So in this realm, you can basically monetize all the devices that you own that have sensors in them. So think of your smartwatch or the sensors in your car dongle, anything that has a sensor in it that's tracking your in real world activity. And in DePIN, you can mine those sensors, share that data with the network to basically earn tokens. So it's a way to monetize your behavior and monetize data that you're already sharing to these networks anyway. The problem in Web3 with DePIN is that oftentimes you're sharing a lot of information to earn those tokens. So your geographical location, some health information, the IMEI and serial number of the device that you're using, all these kinds of things. So we could basically use MineLake, and we did use MineLake as a way to add privacy so that you're not sharing all that data in order to earn those tokens. So that's kind of the first component to think about what we do. We then started looking at other addressable markets, and we realized kind of broadly that Web3 is really great at decentralizing trust, but not so much yet at decentralizing security. So a lot of security is still provided by Google and AWS and Semantic in Web3. And so we try to sit in the middle where we can bring FHE in a really applicable way to decentralized security in Web3 as well. And so this is a huge market, right? There's about $1 billion every year occurs in data leaks, front running, and hacks in L2, in Web3 between L1s, L2s, bridges, and DApps. And then we have about $30 trillion is the estimated regulated crypto market. And $17 trillion is what the AI economy is priced at currently. So the AI economy that takes personal data. So the data that feeds the training of algorithms in order to produce models is a pretty massive market as well. So we have a novel approach to applying FHE to secure all of these markets. So we do use ZK as well because ZK has definitely brought great scalability in Web3. But in terms of the composability and the real feature that we bring that we think FHE is bringing to Web3 is on-chain computation. That's the big one. So ZK in Web3 has the issue of basically putting the proof on chain, but the actual computation happens off chain. So there's a trust assumption there. And so with FHE, we can actually bring that on chain, which solves a really big problem and will increase composability. And what we find in Web3 right now at its current stage of maturity is that there are so many brilliant minds solving the problems of today, but we do have problems of tomorrow that we have to start thinking about, which is quantum computing. So the great thing about FHE, as we know, is that it's quantum resistant. And so building quantum resistance into tech stacks, I think, is important to think about now. And so what we're doing to break into the market, like I said, we're one of the first tokenized FHE projects. There are several others that are really worth looking into, like Phoenix and Inco. But what we're really interested in doing is showing the market, showing users all the different applications. So we kind of have an FHE computation network, which is the supply side that you see on the left. But we've also started launching our own DApps to help with the demand side, to kind of help bootstrap the demand side because we're so early to the space in Web3. So you can think of basically applying FHE to chains and rollups. So think of basically staking and restaking. If you're an institution, if you're a bank, or if you're a money manager of any kind, and you're starting to allocate to like staking Ethereum or any kind of proof of stake consensus mechanized network, you're basically sharing, it's very public how much of those rewards you're earning. Once somebody sees it has a wallet address, they can, anybody in Web3 can see the rewards. So these institutions are interested in having a layer of privacy, but also on the user side, if you don't want all of the income that you're generating from Web3 public, having FHE is really important. So that's one really hot new use case, staking and restaking in Web3. Obviously, adding FHE to the protocol layer. We've already integrated at the storage level with Greenfield, Arweave, IPFS. So our current data lake is really used for cold data, but with these decentralized storage service providers, we now have the access for cold data as well. Did I say cold data? Hot data. We're intended for hot data, but with these decentralized storage providers, we now can offer cold data as well. It means you can store your data over the long term, keep it encrypted, and run compute upon it, right, without decryption. And then bridges are a really hot topic in Web3. So in order to really onboard the masses and to get Web2 users more comfortable with Web3, we need to lower the barrier between chains. So we need assets and liquidity to be able to flow across chains more seamlessly. So bridges have been the standard for several years, but they also happen to be a quite vulnerable feature of the Web3 ecosystem. And so adding FHE obviously bolsters the security of FHE bridges. And in this, in the last 6 months alone, we're seeing some really innovative approaches to bridges as well. Chainlink, which is one of the best known brands in Web3, launched an Oracle bridge. And there are a couple other projects as well that are coming up with innovative approaches to bridges that reduce the attack vectors. And so we're working with them as well, bringing them our zero trust solution. And then FHE for AI. So like we talked about earlier, with the training of algorithms, you're scraping public data. So the issue there is that data then, of course, lives on somebody else's server and it's not encrypted. So if we can encrypt that data and still allow for processing, I think that's the best world for all parties involved, including especially those who are contributing their data to train the algorithms. So this is a little bit of what we're doing on the demand side. There are other use cases as well, and we're finding more of them every month. And what we're seeing is just a early adoption of FHE as a new standard of security in Web3, which I think is really, really exciting. So this goes a little bit into how we built FHE into kind of a data security roll-up for decentralized storage. So this is just kind of a visual of what we did with IPFS, Arweave, and Greenfield. And then, of course, for compliant and on-chain transactions, we proposed FHE in combination with stealth address protocols. So stealth address protocols became popular around 6 years ago as a way to send and receive assets on-chain with a little bit of privacy and increased security. So basically, a stealth wallet is created that helps to mask the transaction so that it's not totally public and publicly available. What we did was we brought FHE to that. So FHE now generates the key pair, stores them on the client, stores them locally on the client side, and now users have the ability to send and receive transactions both on a single chain like Ethereum or cross chain from like Avalanche to SWI or Solana to BNB, and in an untraceable yet verifiable way. And so that's a key difference too, is that FHE is much better accepted by regulators. It does add privacy, but it is verifiable. So there are some solutions in Web3 that are completely unverifiable. They just are, the ZK is kind of siloed and it's completely masked. It's made to be completely anonymous. So we are aware of the fact that we don't want a world in which there's complete anonymity all the time, and you can't even define or identify bad actors. So the fact that there is on-chain computation happening, which is verifiable, that we can look at the batch and some of the metadata and actually determine that this is what's happening here with a certain transaction, we may have identified a bad actor, is really, really critical. So this solution, which we call MindSap, has won a hackathon, and we currently are going to market with this as well. So this also bringing some stealth to just transactions between chains and on single chains. And I'll touch on one last really interesting feature, which is that in Web3, the current popular theme and narrative that I think is going to last for quite some time is called RWA, so the tokenization of real-world assets. And a lot of the real-world assets that we've seen that have been tokenized to date are treasury bonds, particularly US treasury bonds, as well as natural resources within geographical parameters. So, gold, silver, commodities that are in a country's geographic bounds. And what we're finding is that, so first of all, these are really massive asset classes, billions, hundreds of billions of dollars, and they're tokenizing primarily on private chains first, which means that they're tokenizing on bank coins, either central bank coins or private bank coins, and they're not available to the market yet. So what is a need from the bank side is eventually to have public chain liquidity. So to be able to encourage public chains and public chain users to interact with these products to increase liquidity. They know in order to do that, they have to have a better level of privacy so that users aren't completely engaging in just a surveillance mechanism. And also there's a level of security that FHE provides in the actual tokenization process, which we're finding is really valuable. So this is a really big narrative right now, and it's playing out in real time. We're working with some of the leaders in the world on this task, including nation states as well as some of the big banks that are doing this tokenization. And it looks like we have a really actionable solution. And then this is our kind of latest product that we've been working on that I mentioned earlier. So again, in a really big another theme in Web3, of course, is staking, the rewards that you earn for staking or helping to secure a network. So even a lot of institutional investors are staking Ethereum, for example, and they're earning 4 or 5% per year pretty steadily as Ethereum kind of becomes the world's computer. And the problem with that capital is that it's locked up in Ethereum, and they're finding that actually if you're staking Ethereum, you should be able to restake and help to secure other networks. And so that's the concept of restaking, is using the same tokens to secure not only one network and earn rewards there, but also secure another network and earn a separate batch of rewards. Also, basically being able to double up on the return on your investment. So we partnered with AltLayer and EigenLayer to basically double and triple the rewards by adding FHE to the staking process, which is a level of, again, security and privacy, to make this whole process more secure. So this is a really exciting theme as well happening in Web3. And then touching back to the AI, we did actually launch a DApp as well, again, to kind of bootstrap this. So Mindex makes a call to ChatGPT, and you can interact with ChatGPT through Mindex, but your chat history and your prompts are stored locally. So you don't actually share that data back to ChatGPT. So this is really crucial. We know that the latest studies are showing that a lot of LLM users are using LLMs for work, and they're sharing sensitive IP with OpenAI, which OpenAI and Gemini and Bing and all the rest, they tell you not to do, but it's hard to work with that if you're in the middle of your day, you're trying to get work done, and these LLMs are incredibly resourceful tools. So it's hard to keep track of what you're sharing and what you're not sharing. What we've done is basically allow you to encrypt those chats and those prompts on the client side. And so what we see happening is basically a broadening out of the prompt marketplace, specifically in AI. There are definitely other components that need decentralization and better security in AI, but the most immediate could definitely be prompt marketplaces. There are a couple examples right now that are up of prompt marketplaces, but this really should be a very broad, rich, data-rich environment, and I think prompt producers should have the ability to kind of own and potentially even monetize their prompts. So that's an exciting use case, and that obviously AI is going to be a trend that will be with us for quite some time. So we're continuing to build out applications into this vertical. So yeah, and then just to wrap up on my network, we're basically an A-stage company. We had a successful seed round closed over the summer, and we are off to the races. This will be a big year for us in terms of announcements. So that's a little bit about us. Feel free to ask any questions.
Awesome. Thank you, Christian. Yeah, and any questions, share in the chat or pipe up. Oh, we got one here. Asking, so don't you work on the Zama stack? Isn't it limited to encrypting 8 to 16 kilobytes of transaction data? And how does mine do all of this with the available resources?
Right, it's a great question. So we have partnered with Zama, and they're helping us with our Mine Lake rollup product. There is a piece of development specifically in AI that is contingent upon hardware acceleration. So we haven't touched those areas yet. But for right now, we're not using FHE for the entire tech stack for every single process. In stealth address protocols, it's generating the key pair. And so the time, the TPS on that, the transaction time is milliseconds. It's still fast. So we're using FHE in all the areas where finality can be achieved really quickly. To the question, which is a good one, there are still areas where hardware acceleration is necessary. So we still, we are at least a few years away from having FHE wide, FHE completely, front to back, full stack FHE enabled tech stacks. But for right now, there are these few applications that we've listed, and all of those basically have really quick processing times.
Okay, cool. And there was then a follow-up about, so are you running your own FHE scheme, or are you using the sort of Zama one out of the box?
The answer is both. So we have different, we went through a number of DApps that we've launched. So on the supply side, we have FHE rollups. We're using Zama for one of those. But for the other ones, we have our own. We're using adaptive fully homomorphic encryption, which is kind of like an ESG version of encryption that just selects the best computation method and reduces noise as you scale up the processing.
Gotcha. Thanks for the questions, S. On my end, I'm curious to hear more about the data lake. So where do you see this unlocking potential avenues for more sort of like data collaboration and stuff like that? or is it very much still sort of siloed data?
So do you mean like in terms of applications, verticals, what specifically?
Yeah, no, just wondering how this sort of can help sort of increase collaboration, right? To have everything maybe in like a public network, like transparently but privately.
Yeah, well, I think the feature of, I don't know if this answers your question, but I think this feature of like the shared state in FHE and allowing for third-party computation is kind of scalable. That's a more scalable, I think, architecture than just using ZK. And you can think about, I mean, the real big use case, the most apparent use case that we found really quickly was like every single bank in the world spends, I think it's $57 for KYC and AML. And long ago, and there was a presentation at Mainnet where a representative from Euroclear was speaking to this. 20 years ago, the banks got together and said, hey, we're all spending $57 per client. And a lot of our clients bank with each other. Like, you know, there are people that have bank accounts with JP Morgan and Citibank. So is there a way we can streamline this so we're not all spending money on KYC? And they worked on it for many months and they couldn't find a way to do it because there was no shared state for this kind of thing. But that's what FHE offers. And so in this new world, you can bring down cost because, you know, the analogy with ZK is that if you and I go to a bar, bartender needs to see, or the doorman needs to see that we are of drinking age. So he asks for ID. And instead of showing our birth date, we're showing our home address, our height, our weight, all this other information that he doesn't need to see. ZK encrypts just the birth date, gives him the proof. Okay, that's great. But what happens if we go to another restaurant? As we go down, every single doorman has to run this compute over and over again. In FHE, you don't have to do that because they can verify the compute that the first doorman ran. So in that sense, there's a level of scalability to this in very simple ways like KYC, AML, KYB information that I think will take off like wildfire and already is starting to.
Okay. Yeah, interesting. The KYC approach is a cool one. We've got another question, this time on the sort of AI side of the products that you presented towards the end. So are you sending encrypted prompts to ChatGPT, or how do you how does MindX incorporate FHE now?
Right. Yeah. So they still have the so ChatGPT can run compute on the encrypted data. So yes, if that scales up, you know, that would change the industry, obviously. If we had millions of users that were all encrypting their data, that would definitely change the model. So it'll be interesting to see what happens, ChatGPT's model. But yeah, for now we encrypt that data and it's stored locally.
Sorry, I'm not sure I understand the response. So you are working with ChatGPT, right? So I guess your answers have to go to them, or do you have a model locally, and how does that work?
So we make the API call to ChatGPT. We're not working with them closely on this project. You'll have your prompts and your chat history stored locally in ciphertext or in plain text. So it gives you that ability. You still will share an encrypted version of that with OpenAI.
And they can run an inference on encrypted inputs?
Potentially, yeah. That's really on their end. So the way we kind of look at it is like it's their problem to figure out. We like the fact that if the client side has the ability to encrypt the data locally, that's kind of the win that we're trying to achieve.
Okay, so I guess you've done the sort of setup on your end, but it doesn't actually sort of like work. You can't privately send your data to ChatGPT.
Yeah, that's correct.
Okay, all right.
Yeah.
All right, any other questions? All right, Christian, thank you so much for presenting it. Always cool
Thank you,
to see
everyone.
a blockchain project in here working on FHE. On that point, if anybody is developing FHE, we would love to talk to you. You've seen all the great stacks you can build on. So yeah, looking forward to seeing people developing more on top of these. We'd really like to thank all the presenters that were here today from sort of all these varying time zones. And we appreciate everybody accommodating the 2 to 4 CET slot. With that, we'll share all the resources on the channel. Thank you so much, everybody, for attending, and feel free if you have any more questions to continue the discussion on the chat.
Thank you. Thank you very much.
Bye, everybody.
Bye-bye.
Thank you. Bye.